assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
Here's an example of integrating over a charge distribution to find potential due to that at a certain point. And we are going to be starting with the expression for a point charge potential, but we are going to consider it broken up into little tiny pieces due to infinitesimal point charges in the source. So we will add up the contributions for each of those little point charges. So the source is lying in one quadrant of a uniformly charged surface disk. And we're told that the initial disk had a uniform charge, and then we removed 3/4 of the circle. So we're left with one quadrant. So we could have found the potential due to the full circle, but we'll see that it's not too much more difficult to find for a single quadrant. Okay, but the idea is that there's a little dq sitting in the surface, and we are going to be using an area to keep track of where that source charge is and adding up contributions through integration. So dq in this case can be written as a surface charge density times a little differential area. And I'll try to show, this may be exaggerated, but a little differential area. Okay, this is not going to look too good. It's got one side that's an arc length. So I'll show that side is r d theta using an arc length gives the two sides that kind of go tangentially. And then dr is the width going in and out radially. So d area is just r dr d theta. And that may look horrible that we're going to have to integrate over those two variables. But we've got one more thing we have to put into the potential, and that is this curly r. What is curly r? Curly r is a position vector that connects your observation point to your source point. So imagine a vector that starts in the disk. I can draw it, but it may look a little yucky. Starts in the disk and points directly up to point P. That is our R vector. And we can simply find it. Our observation point, we're told, is up the z-axis. And let me be clear, the xy plane holds our quadrant, and the observation point is up on the z-axis, up there. Okay, so our observation point is 0, 0, d. Our source point is down in the circle. So that is simply our cosine theta, our sine of theta, and 0. We'll put everything on the z-axis out of the disk. And then we can simply find the magnitude of that by taking the sum of the squares of all the components. And we get r squared cosine squared plus little r squared sine squared plus d squared. Pythagorean theorem coming into play. And so nicely, that does not involve the theta. And it is the last piece that we need in our integral. Okay, so we finally have dV is equal to K, the electrical constant, times sigma, a constant given to us. And notice that the surface charge density is not going to change by cutting the 3 quadrants out. And then we have the integral r dr. I'll put d theta separate, going from 0 to pi over 2. And then we have curly r down in the denominator. Okay, so that's not going to be too hard to integrate. D theta between 0 and pi over 2. We should integrate both sides. And really what we're doing is adding up things in a continuous way. So the theta integral pops out pretty quickly. We'll have to mess around with the r integral. The easiest thing to do is probably a substitution. I see that the denominator has a nice form that if we let r squared plus d squared is equal to u, then 2r dr is du, and we basically have the integral of 1/2 du, u to the 1/2 downstairs, and u goes from the d squared up to big R squared plus d squared. Just putting in for our limits. And that's not too hard to evaluate it. I'll show the final result. There's some, integral of 1 over u to the minus 1/2 is u to the 1/2 over 1/2. Yeah, so we have some factors of 2 that go away, thankfully. It's always good to make those go away. But we're still left with pi over 2. And then we have r squared plus d squared to the square root minus d squared to the square root. We can simplify that. Okay, and now it's just a matter of putting in our numbers. We are told the radius, we are told the distance d, and the electrical constant is always a known. Let me see, r squared plus d squared. We can figure that out. And then subtract d. And if everything's in SI units, oops, I forgot the density, didn't I? That's very small. 7.73 times 10 to the minus 15 for femto. And that is all in SI units, so it should come out in volts. And I will just check those numbers just because they are kind of crazy. Yeah, and it's a pretty small potential. I'll leave it in terms of pi. That way there can be a little bit of a check on some of the numbers. So not a lot of volts there. Fraction of a millivolt or a few microvolts.